on the third lectures of Professor Andrea's due. On the last 2 days, we learned about the learning systems. Now today, we'll be going to talk about the glassy dynamics and plasticity based on this machine learning.
Yeah, so today I'm going to talk about a totally different problem, which is to understand glassy dynamics and plasticity. We're basically going to tell you how we develop phenomenological theories based on a machine learned quantity. Okay, so it's sort of a hybrid machine learning theory approach to the glass transition and plasticity. So that's this third thing, this third lecture. And again, it has this theme of doing statistical physics in a very unconventional way. This time to tackle a problem that really has, all three of the horrible complications that I talked about before, being far from equilibrium, having complex landscapes, and correlated disorder. So, and to just highlight the people who have done the work in this first part that I'm going to talk about, particularly want to highlight two of them. Oh, I'm sorry, I bolded this, but maybe only in this slide. Okay. So Indrajit Ta, who's here chairing the session, and Sean Rideout, a graduate student who recently finished in my group. But this sort of whole approach, or this machine learning approach, I should say, was pioneered by Sam Schoenholtz in my group and Dosh Chubuk, who is a student of Tim Kaxiris and a friend of Sam's from college. And they actually tried machine learning on glassy dynamics and showed that they got 90% prediction accuracy before they even told me about it. So they really deserve a lot of the credit. Okay. So, the big difference between liquids and solids, right, is that liquids flow and solids don't, which means that when you apply a stress to the flow, it relaxes in the liquid, but not in the solid. And the time it takes for that stress to relax is what I'm going to call the relaxation time, TAP. Okay. Now, how does that stress relax? It relaxes by rearrangements, where particles change their neighbors, right? And that's what doesn't occur so often in a solid. Okay, so the liquid to glass transition occurs when you cool a liquid. Okay, when you do that, the particles remain in disordered configurations while the relaxation time increases not only continuously, but extremely rapidly, often 10 orders of magnitude and just tens of degrees. And so when people, run out of time to measure the relaxation time, so the system can't reach equilibrium, it's by definition far from equilibrium. At that point, the system is called a glass. Okay, and this is universal, that all liquids undergo glass transitions if they can be cooled quickly enough so that the crystal doesn't nucleate and take over. And because of that, it really is a universal phenomenon. And, the idea is that a universal phenomenon needs a universal explanation. And that's really what we're after here. So, as I said before, right, the goal of statistical physics is to do this huge dimensional reduction, but to the right microscopic variable. For example, the order parameter is something that really captures what you want to know about the collective phenomenon. And these problems of being far from equilibrium, having complex landscape and correlated disorder make this problem very difficult. So the one I haven't talked about so much, that's the glass problem. The one I haven't talked about is the complex landscape. So this is a nice landscape, right? But it's, the height versus two position coordinates. Of course, we're talking about a landscape which is the energy or the free energy in 3D coordinate landscape. Okay, so sorry, 3n. 3 dimensions times n dimensional landscape. So this landscape, right, has of order e to the of order n minima. That's huge, okay? Even for 1,000 particles, that's about 10 to the 1,000 minima. And so it's incredibly difficult to map out. People have been able to map it out numerically for maybe up to 60, 80 particles now, but that's about as much as you can do. The problem with this is that the properties that you see then are linked, are really completely depend on how you explore this landscape. All right. So, and rearranging a particle requires the system to jump over an energy barrier. So it's going over a barrier in this landscape from one basin to another. How do you describe this problem? Well, we're going to think about this first in terms of temperature. Okay, in temperature, you can view that as sort of setting a rough height in this landscape. As you lower the temperature, you're lowering the height at which you're exploring the landscape. And so as you lower, you get stuck more and more in these minima. But another way to explore it is by just dragging the system through. In other words, by applying some shear, okay, then you drag the system through the landscape, you deform the landscape so that you just, if you're doing it at zero temperature, you're deforming it so that you're always sitting at a minimum. But by doing this, you go from one minimum in the unsheared landscape to another. Okay, so you rearrange that way. All right, so let's first think about temperature. So what are the phenomena that we want to understand here? Well, I'm going to focus on a few, okay? There are many more phenomena associated with the glass transition. I'm just going to restrict myself to some, all right? So at a high enough temperature, you have an ordinary liquid. And what we mean by that is that the relaxation time, for example, has the expected dependence on temperature just from having an energy barrier, e to the energy barrier over temperature, okay? I have the word Arrhenius in my slides, but I actually try not to use it. It's sort of impossible, but I try not to use it because I recently just did not know this history that Arrhenius was president of the Swedish Academy when Marie Curie was awarded her second Nobel Prize. And just after that, a scandal broke out because she was having an affair with Langevin. And people in France got very upset. And he actually wrote to Marie Curie and asked her to turn down the Nobel Prize to save the Swedish Academy from embarrassment. And so now I don't like him anymore. Okay, so, but it's just a Boltzmann dependence, expected Boltzmann dependence of the relaxation time on temperature, right? But if you go below something called the onset temperature, right, the relaxation time develops a stronger than Boltzmann-like dependence on temperature, as if the energy barriers are getting higher as you lower the temperature. Also, the dynamics become spatially heterogeneous. And then below this, there's a glass transition where the system falls out of equilibrium. Okay? So the standard picture, I mean, this is the picture, and by 2010, it was even enshrined in a book called Dynamical Heterogeneities in Glasses that came out of a workshop in Leiden, which is that really there was no real connection between structure and dynamics. And the evidence for it was, for example, the structure changes very little, while the dynamics can change by many orders of magnitude. Okay, people had searched for probably 5 decades by then and found no structural signature of the glass transition and no structural signature of kinetic heterogeneities, which I think I'm going to mention shortly. Okay, but the point is that it turns out to be a trivial task for machine learning to find that structure dynamics connection. People had tried for 50 years and failed, but machine learning found it like that, okay? Even the simplest, dumbest machine learning method works. Okay, so what do I mean by this faster than Boltzmann-like increase of the relaxation time? Well, if you plot the log of the relaxation time, this is log of viscosity, but it's the same thing. Log of relaxation time versus 1 over temperature, okay? then you would expect it to be a straight line if it were just Boltzmann-like, okay? And what you see is that for many liquids, it's not a straight line. It shoots up very, very rapidly, okay? So this is the famous angel plot named after Austin Angel, who died recently. So some glass formers, like window glass, silica, and so forth, are called strong glass formers. It's a stupid thing, stupid nomenclature, but they're nearly Boltzmann-like. And others are fragile. They have this very strongly non-Boltzmann-like dependence. So it was discovered by Shrikant Sastry back in 1998 that for these fragile liquids, the ones with this sort of behavior, it's very interesting that if you look at the effective energy barrier, it's flat above a certain temperature. So there's this well-defined energy barrier. That's why you see Boltzmann-like dependence, okay? But below this onset temperature, it shoots up so that the effective energy barrier depends on temperature, okay? The energy barriers get higher as you lower the temperatures, okay? So, and the cool thing is that it happens at a characteristic temperature, which is the onset temperature. The other thing that happens at that special temperature are kinetic heterogeneities. Above it, it's homogeneous. Below it is spatially heterogeneous. You see this even in traffic. If you're well below the onset of jamming, right, everybody is going pretty much at the same speed. Well, not in India. Okay, but if you just had cars, okay, people would be going about just the same speed, roughly a Gaussian distribution of speeds, right? Nothing special. But as you get closer and closer to the onset of jamming, right, it's always you're stuck and the person in the next lane is going. That's a spatial heterogeneity, that a kinetic heterogeneity, that in a given interval of time, the distance that you move depends, it becomes a highly non-Gaussian distribution, very, very wide, okay? So, and this is just a movie from one of Doug's experiments of a granular system that's close to that point. And what you see here are particles that what you see are their tracks in that given interval of time, which is the relaxation time, okay? And they're colored according to how far the particle moved in that interval of time. And you see that some of them, right, it's becoming very heterogeneous, that some of them are moving a long way, whereas others are stuck. Okay, so yeah. Yeah. So this is the particles are sitting on a wire mesh, and there's air flowing up through the mesh, and that makes the air flow turbulent, and that turbulence pushes the particles around. So that the behavior in this many particle limit is actually quite thermal, that you can measure many different definitions of temperature, and they all turn out to be the same. Okay, so it is, in this approximation, quite a thermal system. Shriram was talking about it yesterday, that if you just had a single particle in that, it's also thermal. But if you had two of different sizes, they become active, they start scooting around, it's not thermal at all. Okay, but in the many particle limit, it becomes thermal again. And you see the same sort of
Just go ahead.
behaviors. Yes.
No, just one thing. Actually, I mean, more precisely, the point is if you went in and made a sensitive measure of thermalness or non-thermalness, for example, the Harada-Sasa, there is the correlation response difference, then depending on how you filtered it in time, you might or might not see that it's not thermal. So if you blink too often or something, then you'll miss the non-thermalness. So
Exactly.
even when you say it is thermal, actually at short enough time scales, you'll be able to see it.
It's right. It's thermal on long time scales.
Yeah,
That's absolutely right.
In a filtered sense, it'll be thermal.
That's right. In a filtered sense, a long time scale. So yeah, and it was Jorge Kirchan and Leticia Culiandolo who showed that in a lot of these systems, At short times, you see the actual temperature. At long times, it crosses over to an effective temperature, which is quite different. And I was talking about that effective temperature. That's right. So, so how do we quantify that dynamic heterogeneity? Well, we quantify it by this thing called the overlap function. Okay, so what this is you just look at the overlap function, just measures whether the particle has moved more than some distance, which is usually taken to be a fraction of the particle size in a certain time. Okay, so it's 1 if it hasn't, it's 0 if it's moved more than that distance. And so then when you average over all the particles, you get the average overlap. Okay, and at high temperatures, right, it'll decay quite rapidly because, okay, at first nobody has moved, but eventually, you know, rather quickly everybody moves. And this time scale that governs this decay is the relaxation time. Okay, and as you cool the system going this way, okay, that relaxation time gets longer and longer. All right, but you don't have to just look at the average. You can also look at the variance of this overlap, and that's what measures the dynamic heterogeneity. So if you look at the variance, it has a peak, okay? That peak occurs, the peak occurs at the relaxation time, okay, for that temperature, okay? And the peak height, I'm not going to go into details about this, but the peak height measures the degree of heterogeneity in the system, okay? So chi4 star. All right, so that's the way you quantify it. I'll come back to that, remind you. All right, so
Excuse me.
statistical physics, what do we want the system to be able to do? Well, we wanted to reduce it down to a relevant microscopic variable, right?
There is a
Yeah.
question.
Sorry. Yeah, hi.
What is typically the functional form of this relaxation time?
The functional form of the relaxation time on temperature is that super Arrhenius dependence, okay, that I was showing you before, okay.
The plot you showed, was that like linear log plot or?
Yeah, this is linear log. This is a log scale. It's log scale in time and roughly equally spaced, not equally spaced temperatures. They're getting closer together. The temperatures at which we measure are getting closer together as we get closer to the glass transition. Yes. Okay. That data is for the Kolb-Anderson model, which is a binary Leonard-Jones model. Okay, so so now, all right, machine learning, right? It's a natural tool for this because it's designed for dimensional reduction. In general, I think for statistical physicists, machine learning makes a lot of sense because that's precisely what it's designed to do, is dimensional reduction, okay? But the problem is, you know, it was designed by computer scientists to solve computer science problems. We want to solve physics problems, okay? So you had to do dimensional reduction, but you had to do it, you had to reduce it to the right microscopic variable. Okay, that's where, you know, we as physicists come in, okay? We have to think about what is the right microscopic variable to understand the dependence of the relaxation time and the kinetic heterogeneity on temperature. Okay, so this is where we come to this idea of structural predictor for glassy dynamics. Because in an ordinary liquid, any particle can rearrange at any time. They're roughly equal, okay? But in a solid, that's not true at all, right? So in crystals, we know that it's particles at defects, primarily dislocations, grain boundaries, okay, that are far, far more likely to rearrange due to thermal fluctuations, okay? Whereas particles that are deep inside crystalline regions are very, very unlikely to rearrange, all right? So this is why people were looking, you know, for the defects that were responsible for relaxation in a supercooled liquid, right? But of course, because the structure is disordered, you can't define defects the way you would in a crystal. And that was the problem. Like, how do we find these defects? So this is just an illustration from my colleague Arjun Yode at Penn of a colloidal crystal. Okay, here it is far from the glass transition. As you bring it, and you see these grain boundaries here, okay, in the crystal. As you bring it closer to the melting transition, right, where does it start getting disordered first? Where does it start having rearrangements first? It's at the grain boundaries, okay? So this is a blow up, okay? It starts melting from the grain boundaries. And why? Why is that? That's because the energy barriers are lower there, okay? So, all right, so that was the challenge, right? Can we define these defects which have lower energy barriers that allow them to rearrange? And of course, the point is that we can from machine learning. Now, before I go into this, I'm gonna take a moment for philosophical reflections, okay? Which is that what we're doing is we're using machine learning to predict a structural predictor of whether the particle is going to rearrange now, okay, or right away, okay? There's most of the people that have come into this field of looking at machine learning and Glassy Dynamics have been doing something different, which is to use machine learning to find a structural predictor of future dynamics, okay? So in the last few years, a lot of people have been doing that, okay? And that was actually posted even as a benchmark challenge to find the best predictor of future dynamics, okay? And so they want to predict, for example, the dynamical heterogeneity, the magnitude of dynamical heterogeneity, okay, at the relaxation time from the structure at time 0, okay, or relaxation time before, okay? And there's a nice paper, a recent paper about that. Okay, so where at least at that point, they said they had the world record. Okay, another approach, right, that a lot of people have taken is to try to construct the best possible predictor of dynamics, whether it's structural or not. So for example, they use information about the interaction potential, okay? So we don't want to do that. So we have stuck to purely structure. And let me explain why. So the reason why we want to just look at structure is then because we can deduce this in experiments, okay? And we have applied this to many, many experimental systems where we don't know the interactions. Colloidal experiments, you just don't know the interactions precisely enough to be able to do this, okay? To calculate the Hessian, okay? So that's why we want a structural predictor. Why do we want an instantaneous predictor? It's because, of course, the behavior, this is a many-body system, behavior is chaotic. There's not that much you can predict at a later time, okay? And so our approach is let's predict what happens now and then to use theory to understand the statistics of what we expect to happen at a later time. So that's what we're doing. That's a little different from what other people are doing nowadays. Okay, so what is our approach? Our first thing was to use what's called a support vector machine, and I'll go into a little bit of detail about how we do that. But the idea is in the continuum limit, what we're doing is that we're defining softness as some weighted average over the local pair correlation function of a particle, okay? So on average, the pair correlation function looks something like that, right? And we're weighting it in such a way, okay, so that this quantity correlates strongly with rearrangements. And I really want to point you to Sarika's talk later today, where she'll talk, you know, when you write it this way, it sort of lends itself to a mean field sort of liquid state approach. And she's done really nice theoretical work on that she'll talk about later today. Okay, so so we get this quantity softness, okay, and it's interesting, right? It has a roughly Gaussian distribution, you know, as you would expect it to, because it's the sum of many things, okay? It has this roughly Gaussian distribution. This distribution shifts down as you cool the system So the particles get less soft as the average softness goes down as you cool, okay? And it's correlated, it's spatially correlated on some length scale, which is of order the particle size. So it has short range spatial correlations that may correspond to what's called the point to set length. It seems to increase even more slowly than the point to set length. Okay. All right, so what is the meaning of what we're doing? Well, you know, when you look at when you use machine learning and you identify who's who in a photo, right? Oh, this is my uncle. The thing says this is your uncle, right? It's not just using, you know, the horizontal you know, distance between his eyes, right? It's using many, many, many quantities to try to, that are correlated with each other, okay? But it's using these many quantities to try to figure out that, to figure out that this is your uncle. All right, but so that's the idea here, is that you use many, many different quantities, and these quantities are the local pair correlation function at many different radii, okay? So in the simplest example. And then what you do is you use a small subset of your data where you say, okay, I know that these particles are just about to undergo a rearrangement, whereas these other particles haven't had a rearrangement for a very long time, okay? And you use that then to train this thing. How do you do that? All right, so here's your thing. So we have, let's say, m quantities, which are the local pair correlation function at different radii, okay? And now we're going to put this into a high dimensional space. So on one axis, we have g of r at one value of r. Orthogonal axis is g of r at a different value of r, and then a third value of r, okay? So if you have m different values of r, then I have an m-dimensional space, okay? And where I am in this m-dimensional space then tells me about my local structural environment, okay? So that's the idea. Calculate that. Oh, how did I do that? Okay, so that's what you do, okay? Now you go into this high dimensional space, okay? Which here I represented 2 dimensions, and you take the particles that I know that these are just about to rearrange, you color those points in space white, okay? And then you have others that have not rearranged for a long time, you color those points gray, okay? And now you construct the best hyperplane in this high dimensional space that separates white from gray, okay? And for this, then, softness, what we describe as softness, is the distance from the hyperplane. So if I have a new particle that's not part of this training set, right, I can say, okay, what's its local and structural environment? Where is it in this space? The distance from that to the hyperplane is its softness, and it comes with a sign that is positive if it's on the rearranging side, it's negative if it's not on the non-rearranging side. So that's it, okay? So, okay, and there are details about how you decide if a particle is rearranging or not. I'm not going to go into that. It gets a bit technical.
Andrea?
Yeah.
I have a question right here back.
Yeah.
So this is instantaneous in the sense that you're looking at the structure at the verge of a particle making a hop or something like that, right?
Exactly.
So if you go back in the particle's trajectory, so away from where it made a hop, so backwards in time, at what point do you stop making a distinction between a particle that's about to make a hop and that makes a hop in the future? So when does the machine learning thing fail as you go back in the particle's trajectory?
It doesn't necessarily fail, okay? Let me just say, so let me first say the way we choose our training step, okay? So we basically use a time that's a little beyond the cage rattling time,
Yeah.
okay, to say it's going to hop, it's about to hop. So we choose particles that are about to hop on that rather short time scale. And then And then for the ones that are not hopping, they have to not have hopped for a whole relaxation time, okay, going back. Okay, so that's how we choose our training set. Now, if you say, okay, now I apply this to particles, what I extract is not whether or not they have hopped. Okay, it turns out that 90% of the particles that are on this side of the rearranging side of the hyperplane, sorry, 90% of the particles that hop, okay, are on this side of the hyperplane. Okay, so that's something, but that's not a very useful thing. What I will concentrate on is what is the probability that the particle will rearrange based on its softness. And you'll see that's a very strong function of the softness.
Andrea, how do you decide on M?
M, it doesn't depend too much on M. So basically what happens is that, well, I think I'll be showing you. I'll be showing you that very soon. Okay. All right. So, but what I want to point out is that it's really the hyperplane that is encoding the relationship between the structure and the dynamics. Okay, that's where the physics is of what it is. And instead of saying, oh, I think it's bond orientation or order, or I think it's this or that, free volume, you know, all the things that people have tried, right? This we interpret a posteriori. And the nice thing is that because it's purely structure, we can apply to experiments. As I said, all we need is video of particles and we can apply it. And so we have applied it to many experimental granular and colloidal and nanoparticle systems. Okay. The other thing I want to make is that the hyperplane is non-universal, right? If I have a different system with different interactions, I will have a different hyperplane. However, for all the different temperatures for a given system. So for example, I'm going to be focusing in this part on the Kobe-Anderson model, okay? At all these different temperatures, we use a single hyperplane. So we use a hyperplane trained at the lowest temperature, and then we apply it at all the other temperatures, okay? And we can apply a single hyperplane across many densities as well. Yeah.
Lowest temperature, you know, like what was the advantage of choosing the hyperplane at the lowest temperature over any in-between temperature, you know? Because in machine learning, the further away you go from the training set, you know you're going to make errors more actually.
Yeah, so the reason why we do it is because the prediction accuracy gets better as you go down in temperature. So for the lowest temperature, for example, about 95% of the particles are on the positive side of the hyperplane, whereas at higher temperatures, it's a little lower. But it doesn't really matter. We can do it either way. Yeah, just we do a little better that way. Okay. So 90%, okay, good. It's a good structural predictor of rearrangements, right? But okay, so what? Our mission in life is not to predict rearrangements, okay? Our mission in life is to understand something about a collective property. And for this particular problem, you know, we assigned as our mission the job of understanding what is the relaxation time dependence on temperature, you know, how does the kinetic heterogeneity depend on temperature? So the first thing, you know, if you talk to people, the first example, exhibit A, for why, you know, structure doesn't tell you about dynamics is the difference between the Leonard-Jones potential and the Weeks-Chandler-Anderson, where you just chop the Leonard-Jones potential off at the minimum and shift it up so it's only the repulsive part of the potential. Okay, two rather different potentials, right? But we know from the liquid state theory that that these give you very, very similar results for the structure. Okay, but they have very, very different dynamics. So here is the pair correlation function. Okay, In blue, it's the original Leonard-Jones. Red is the WCA, the repulsive one. Okay, almost the same structure. All right, but look at the relaxation time. It rises much, much more rapidly for the Leonard-Jones than for the purely repulsive WCA. Okay, so how can softness possibly capture that change in dynamics? Okay, so we decided to look at that and to try to understand what it was doing. Okay, and the interesting thing is, yeah, the average softness is quite different for these two potentials, right? But if I look at the relationship between the relaxation time and the average softness, it is almost the same. Okay, so what that's saying is that softness is accentuating the tiny, tiny differences in the pair correlation function. Okay, that here, these are tiny, tiny differences, but softness is exaggerating it. The weights, W of R, are chosen to really be strongest where the differences are greatest. And where you see where are the differences greatest? At the peak and valleys. Okay? So that's where the weights are greatest. It's at the peaks and valleys of G of R. Yeah.
We scale this x-axis by an appropriate temperature, energy scale. Then how different will be the I know that there are some change in fragility. I'm talking about
Oh, this thing. Yeah. You cannot get them to collapse. Actually, they're quite different. There's a nice paper by Gilles Tarjus and Ludovic Berthier showing that, that these two are really quite fundamentally different. Yeah. Okay, and arguing that the attraction can't just be a perturbation in this case. It really makes a huge difference. All right, so I would say, all right, in this case, at least the average softness seems to be telling us something about the relaxation time. So that means we're on the right track, okay? This could be the microscopic variable. To get back to now Ranjini's question, it's pretty amazing that if you look at the number of, values of R at which we need to look at G of R, it turns out that if you just keep, this is a binary mixture, so they're AA and AB if I have a central A particle, okay? If you just keep the height of the first peak, okay, for AA and AB, just two of them, okay, you already get to over about 77% prediction accuracy, all right? And then it just gets better as you include more, but it just slowly, slowly gets better as you include more and more. It's not very sensitive. So once you go beyond a certain distance, it's really not going to change very much, okay? All right, so, and actually just with a single structure function, GAA, okay, so what is the probability of finding an A particle at the height of the first peak for the average G of R, okay? That already gives you 68% prediction accuracy. So it's not terrible, okay? All right, and all right. So, and as just I said, this, if I look at the average over the soft particles, the ones on the positive side of the hyperplane, that's in red, compared to all of the particles, that's in black. What you see is, again, the differences are the peaks and valleys. And so what is this doing? I think of this as it's a quantification of the cage, okay? There's this idea that a particle, very old idea that a particle is trapped in a cage by its neighbors. How strong is that cage? The strength of that cage is determined by the height of the first peak, the depth of the first valley, next peak, so forth. And that's exactly what softness is quantifying. Okay, so it's measuring the strength of the cage. All right, so now here's the important thing. If I start now looking at what is the probability that a particle of softness S is going to rearrange, okay? What we see is that probability, okay, is roughly an exponential, has a roughly exponential dependence on softness. Okay, and the prefactor in that exponential depends on temperature. So it's not so great at high temperatures, but as we go to lower and lower temperatures, it's a stronger and stronger function of the softness. Okay, and what you see is that the probability of rearranging is monotonic in softness, right? So it's low if I have a very negative softness. It's much, much bigger if I have a positive softness. So this is the way we look at it, that, you know, what we're looking for is a steep dependence of this on softness. But more precisely, what do I mean by this? So if I look at the probability of rearranging, not for particles of a given softness as a function of 1 over temperature, okay? So for high softness, what you see, it's a straight line. Log of the probability over 1 over temperature, that's Arrhenius or Boltzmann dependence. That means there's a well-defined energy barrier for particles of a given softness, okay? And this is where the physics comes in. This is why this quantity is so useful, is because it's a good enough predictor that we see Arrhenius dependence of the relaxation, of the probability of rearranging for particles of a given softness. And what you see is that, okay, for soft particles, I see something like this. I have a lower energy barrier, lower entropy barrier. For highly negative softness, okay, I have a high energy barrier and a high entropy barrier. Yeah.
Just to be a pain, if you compare this to fragility plots, clearly you see fragility if you look over a big enough range. The same system over some range can look kind of non-fragile. Is there any such issue we should worry about here? That is, if you looked over a larger range at log PR against 1 over T, whether there would be curvature somewhere.
It does not seem to be. That as long as we get adequate statistics, it really is straight, even in the aging system, even when we go even below the glass transition. Okay, so it really is capturing the dynamics well enough to give us this behavior, a well-defined energy behavior.
Yeah, but I'm wondering if there's any possibility of extending the range of 1 over T a little bit more, and whether one
yes.
That's
yes.
the
so we've extended it down to the glass transition, and for you know, where I didn't bring them, but we have results now for the continuously polydispersed systems prepared by Monte Carlo swap by Ludovic Berthier's group, where you have a very large range and it's quite straight.
Okay, thanks.
Whole range, yeah. Yeah, and what I think is important is the spread of that energy barrier, okay? That a better predictor will have a steeper, bigger spread, okay? A steeper delta E with softness, dependence on softness. So really, I think that's actually a good metric for quantifying whether you have a good predictor or not. I'm not claiming that softness is the best, you know? Yeah.
So there seems like a temperature at which probability for all sort of softness is same.
Yeah, excellent. I'll come back to that in a minute. Yeah, excellent.
I was asking the exact
same question. Yes, yes, excellent. Brilliant. That's very significant. Okay, so so the fact that there's a well-defined energy barrier is a huge benefit, right? Because remember, there are of order e to the order n minima in this landscape. And think of all the barriers in all the different directions in this 3-dimensional landscape that you could go over just from a single minimum, right? It's impossible. It's an impossible problem. But this is telling you the energy barrier that the particles actually go over when they rearrange, okay? And it depends on the softness. And I can have a structural quantity that I get from a snapshot, okay, that will tell me that. Yeah.
So where is the e to the power n term is coming from? Like if you were considering only a repulsive potential, then it will also depend upon the packing fraction of the system. Like if the packing fraction is low enough, then there will be large number of minima as compared to like e to the power n, right?
Yeah, yeah, that's why they're order. It's order n.
Okay.
Okay, it's of order n. But we're considering that we're at high enough high densities, which is where liquids are. Okay, effectively, in terms of their repulsive cores, they're above jamming. Okay, they're very, very high. If we went, okay. Okay, so I showed you just the results with Leonard-Jones, but look, here's silica, BKS silica, okay? It's again Arrhenius, okay? So it works on this very strong glass former, okay? Which has very different temperature dependence of the relaxation time. This is data from Indrajit, where he looked at repulsive harmonic spheres, the sort of jamming, the potential for jamming. And you look at this at different packing fractions. Ludovic Berthier showed long ago that you see very different fragilities as a function of packing fraction. So that near the jamming transition, the behavior is quite, you see, the behavior is the relaxation time is pretty linear in log of relaxation time, quite linear in 1/temperature. So well-defined energy barrier. But as you go higher and higher density, okay, it gets more and more super Arrhenius. But you see that for all of these different densities, again, the log of the probability of rearranging versus 1/temperature is Arrhenius for a given softness, okay, for all of these different systems. And here, we're using the same hyperplane for all of the different temperatures, for all of the different densities, okay? So we can compare them next to each other. Same definition of softness for all of them. Okay, this is also, again, data from Indrajit. This is for the vertex model of tissues, epithelial tissues, used for in a lot of biological physics problems. This system is unusual because it's actually sub-Arrhenius. It's as if the energy barriers get smaller as you lower the temperature, okay? And again, in this system, you see that for a given softness, the behavior is Arrhenius, okay? And then here, okay, is systems that are not glassy at all. These are aluminum polycrystals. I mean, these are simulations done by Spencer Thomas, who's a graduate student with my colleague David, former colleague David Strolowitz. Everybody's his former colleague because he never stays anywhere for more than a few years. Anyway, so they are really serious, okay? These were simulations with 58 million atoms. It was crazy, okay? But they're aluminum polycrystals, and again, you see that if you get to a low enough temperature, the behavior is again Arrhenius, okay? So this softness itself, right? Softness is non-universal. The definition of softness is it's the same for all of these different temperatures, right? But it's different from aluminum than for the vertex model, right? And yet, right, the emergent behavior of softness, the fact that it captures the energy barriers, okay, and is universal, okay? And it's universal from the whole spectrum from order to disorder, okay? Across the spectrum from sub-Arrhenius to super-Arrhenius behavior, okay? And so because of that, okay, I would argue that that's reasonable as a universal sort of description for a universal phenomenon, okay? It's a reasonable starting point, okay. All right, so the consequences of this. So you see here that the energy barrier is roughly linear and the entropy barrier roughly linear in softness, okay? So it looks something like that. All right, now let's stick that into this expression, okay? And what do you get? So just stick these dependencies into this expression. You can factor it into two terms. One of them doesn't depend on softness, okay? That's supposed to be a minus sign. Sorry, not an equal sign, okay? But this term is purely Arrhenius, okay? Doesn't depend on local structure at all, Okay, then there's this term that depends on softness. Okay, that's the term that I said, remember, we have roughly exponential dependence on softness at a given temperature. That's this coefficient here. Okay. But you look at this coefficient, you see, aha, there's a temperature at which this becomes independent of softness, where this coefficient is 0. That's S1 over E1. Okay. What is that temperature? That's exactly the temperature that you guys were pointing at. Okay. It's this temperature, right? This is where the probability of rearranging is independent of softness. It's the same for all softnesses. Okay. And what is that temperature? That temperature is the onset temperature. So here's the onset temperature that you measure from the kinetic heterogeneities. This is a paper by Aaron Keyes, Sharon Glotzer, David Chandler. So they measured the onset temperature in a totally different way. We compare it to our onset temperature. The dotted line is equality of the two. Okay. And that is this temperature where the energy barriers start getting bigger as you lower the temperature. Okay? And the temperature at which the dynamics become spatially heterogeneous. Okay, so now we're ready to tackle then kinetic heterogeneities. We've got the tool, okay, in hand. So how are we going to calculate this? Yes.
So there are various ideas that close to the mode coupling, something qualitatively changes in the way particles move. So does softness tell you something? Does something change in the way softness behaves as you get close to the mode coupling crossover, or is it not sensible?
We do not see anything like that. Okay, as we go close to the mode coupling temperature. So, you know, this is, I have now, there's a very talented undergraduate, Shang, okay, who's visiting my group and is working with Rahul Chacko and Sean Rideout on this, on the polydispersed systems prepared by Monte Carlo swap, where we have, you know, really good data getting very close and going beyond the mode coupling temperature. And okay, everything, this description that I told you seems to be the same. Okay, it doesn't seem to change.
Andrea, I have one question.
Yeah.
So related to what Rajesh asked, so close to this MCT, maybe let's say in terms of energy, MCT energy, there you see that you go through a transition, not a crossover in some sense, from barriers which has multiple unstable directions versus barrier which has one direction. The saddle index becoming 1 below certain temperature, which seems to be very close to the MCT transition temperature. So do you see some signature of those even in the softness?
No, I would say not. I mean, again, we're only looking at the barriers that the system actually goes over. Okay.
I
So
agree
we
that.
don't know how high dimensional that is at higher temperatures compared to lower temperatures, right? The other thing I would say, you know, one thing that Rahul Chacko has found, this is in work that we did with Olivier Dochot and Julie Baroli and David Reichman, is that when you start getting below the mode coupling temperature, you see a crossover to where elasticity becomes important. So elastic facilitation of rearrangements becomes important. Okay, so that's the one thing that we see. So,
but you don't expect that the qualitative nature of the barrier will be different?
It doesn't seem to be very different as far as we see in this.
No. You can have a local definition as well. Anyway, okay, we can discuss later.
Yeah, we can discuss that later, but I mean, so far we do not see
any such signature,
any such change
Yep.
in this. Okay, so I just want to remind you of the overlap parameter and this. And so what we want is to be able to have a theory that captures this, okay? All right, so now I'm going to talk about the softness space theory of glassy dynamics, which is the work of Sean Rideout. Okay, so it is the following. if we have softness, which quantifies structure, okay? And from softness, we have, and from our calculations, right, we have the probability that a particle of a given softness will rearrange, all right? But here's the thing. When a particle rearranges, it changes its own local structural environment, so it'll change its own softness. It will also change the softness of innocent nearby spectators, okay, because it changes their local structural environments, okay? So, and that's facilitation. That's what's called facilitation. So what we need to do in order to have a theory is to understand that interplay, okay? How does rearranging change a particle's softness, and how does it change the softness of spectators, okay? Now, the thing that's difficult about this is that we're in thermal equilibrium, or at least local thermal equilibrium, and so the changes of softness that you get to rearrangements have to be consistent with detailed balance, okay? And this has been the thing, and this has been something that people have not been able to include in models like this. This is non-trivial. There is no Hamiltonian for the softness, right? It's just this machine-learned quantity. So how do you do this, okay? Well, it turns out, yeah. Yes, each particle has a softness.
When the softness of the spectators, that is it referring to softness of the global picture?
No, it's referring to the particle's individual softnesses. Because if I'm sitting here and this particle rearranges, my local structural environment has changed. My local G of R has changed, and therefore my softness has changed.
Then how then the softness for the particle and softness for the spectator both are different? They both are the same, I think.
No, this particle's softness and this particle's softness are different because they have different local G of R's. The origin is different, right? They're different particles. They are surrounded by different particles, and therefore their softnesses are different.
Then spectators means
it's a particle that's nearby.
Okay, okay.
Yeah. Not necessarily the first nearest neighbor, but something just, within the radius in which we define softness, which I should say is 3.5 particle diameters. Okay. All right. So, and it's not very sensitive to 3.5. Okay. So what enables us to solve this is that the distribution of softness is nearly Gaussian. Okay. And the probability of rearranging for particles of given softness is approximately exponential. Okay, so when you multiply an exponential with a Gaussian, you get a Gaussian, right? Just end up shifting the Gaussian, and time reversal invariance, implies a relationship between the change of softness if you go forward and if you go backwards. Okay, and it turns out that you can use Bayes' formula, okay, to close the equations. Okay, I'm not going to drag you through it, but I'm just going to tell you that this works. Okay, and you can then extract the probability for the change of softness of nearby particles. So this is a matrix. I'm going to define a matrix delta S. Okay, so let me, I'm going to imagine implementing this, for example, on a lattice. So I have a site, a lattice site, okay, I, which are lattice sites, they're indexed by I. And so then I have a vector, S is a vector, okay, delta S is also a vector, okay, and I have the probability of getting a given change of softness, okay, for particles in this vector for all the different sites, okay, which then has this form, it's a Gaussian, okay? And what Bayes' formula does is imposes constraints. It tells you basically what the shift of softness should be, and what the mean of this distribution should be. So it's sort of interesting. Well, okay. How am I doing? Yeah, I want to get a little bit to plasticity. So So, and as expected from all of this, the correlations, delta S basically decays exponentially away from the particle in space. Okay, and that we confirmed by our simulations. It's exponential, so this all works nicely. Okay, so you can close the equations. And then you can implement it on a lattice, as I said. So now we can take these closed equations, we divorce it from the particles, we just take these equations, okay, we implement them on a lattice. And it's like a elastoplasticity model, except there's no elasto. It's a thermal plasticity model, okay? There's no elasticity here. And here are the results, okay? So the theory is the blue, the MD simulations are the black. And so the average softness, not bad, you know, agreement, okay? Here's the overlap parameter. The theory is the dashed lines, the simulation is the solid. Again, pretty good, okay? Here's the chi4, the kinetic heterogeneity. You know, not perfect, but again, not bad. The relaxation time, okay? The height of the peak, chi4, a little bit off, okay? The thing that's the most off, but has the right temperature dependence, is the correlation length of the kinetic heterogeneity, okay? The 4-point correlation length, okay? This thing increases for both of them with about the same temperature dependence, but it's off. If you wanted to use numerology, it's off by a factor of about 4. Now, it takes actually about 4 particles to have a rearrangement. We're assuming each particle can have a rearrangement all by itself. And so what Sean is doing now is to generalize the theory to having 4 particles participate in a rearrangement. The preliminary results is that it seems to fix that, okay, without destroying everything else. So, but I haven't seen it myself. He just tells me. I haven't seen it yet. He's working on it still right now, even though he has graduated. But okay. So, all right. So why was machine learning useful here, right? That this statistical physics approach using machine learning, I think, is useful. Okay, it gives us insight. It was designed, right, for dimensional reduction, and it's really, really good at finding the very, very subtle correlations that traditional physics approaches can't find. One thing that we can do once we have that model is we can play with it, and we say, what if we leave out this? What if we leave out that? So if you leave out the facilitation, for example, okay, so you leave out that delta S piece, what you find is that you completely destroy this agreement, that the chi4 star becomes absolutely flat with temperature. Okay, so you need that correlation with nearby particles. So you can play around with it and say, okay, let me take this away, let me take that away, what changes? Okay, and I'm not going to drag you through all of that, but that's where you know, wallowing in the physics becomes fun. Okay, so that's that. Those are the people who did the work I mainly talked about today. I want to say a few words about plasticity. Okay, okay, it's not too bad on time. This is the softness theory of plasticity, and we have a paper that was just accepted in PNAS about this. So now I'm going to think about dragging this ourselves through this landscape, or really deforming the landscape, so that you can tip from one minimum to another. You deform it so that you can go from one minimum to the other without ever going over an energy barrier. So this is doing this at 0 temperature, so I'm always sitting at a minimum, okay? And shearing infinitely slowly, athermal quasi-static shear, okay? So that's a different way to explore this landscape. And you remember I said, oh, the difference between liquids and solids is liquids flow and solids don't. Well, I lied, okay? And you can see that solids can flow. You can take a spoon, right, and bend it. And when you're bending it, the spoon is flowing, okay? Atoms are rearranging. You're inducing. And what does it look like? Well, for so-called ductile solids, that's like when I'll show you the difference between ductile and brittle in a minute. Okay, if you look at the stress versus strain, what you find is that initially, right, for small strains, the stress is linear and the strain, it behaves elastically. It says, oh yeah, I'm a solid, no problem, okay? But if you put a stress that's too large or strain it too far, right, this bends over. And then it flattens out, it starts flowing, okay? So, so that's what it does on average. If you look at an individual, so do you see, oh, see a solid response, sorry. Yeah, that's the liquid or plastic response. And there's a point in between, okay, where we say that's the yield stress. That's the point at which it starts to yields and starts to flow. Okay. This was in Trieste, Shuram was there. Many of you were there in Trieste. Doug was talking about the yield stress of foams, because foams do this. And I was sitting right behind Jacques Pro and Armand Ashdari, and Doug was saying, oh, if you push a foam just a little bit, it resists, but if you push it too far, it will yield. And Jacques turned to Armand and said, just like a woman. Okay, friends. And then he turned around and he saw me staring at him. And he said, oh, just like a person, just like a person. Okay, so this is just like a person. Okay, you push on them too much, they can yield. Okay, yeah, he was very embarrassed. I'm very pleased about that. Okay, so the stress, as you see, has these, if you look at an individual configuration, this is the average behavior. If you look at the individual case, it's much more interesting, right? What you see are these little stress drops, okay? Where you have not just a single rearrangement, but one rearrangement can trigger another and another. You get these avalanches of rearrangement. You get what's called crackling noise. Okay, so if you look at many, many different systems, some are brittle, some are ductile, you know, they have very different behaviors. They have very, we looked at simulations of atoms, Leonard-Jones, silica, okay, simulations of short polymers. Experimentally, we looked at two different colloidal systems and grains and foams, okay? In all of these systems, you can train for softness, okay? And you find softness does pretty well for all of them. They have very, very different interactions, these kinds of systems, okay? And the source of the rearrangements is very different. Some of them is from thermal fluctuations, some is mechanical load, but all of them were either below or near yield, okay? And the interesting thing, oh yeah, and these systems, if you look at the particle size, it spans over 7 orders of magnitude. The elastic modulus spans 13 orders of magnitude in these systems, but they all look the same in the sense that if you look at the correlations of softness, the correlation length of softness, okay, it is basically set by the particle size. So it just scales with the particle size in all of these different systems. If you look at the correlation length of plasticity, okay, it also is correlated on that same length scale. So here's the ratio of the correlation length for plasticity to the correlation length of softness as a function of the diameter of the particle. So again, this spans over 7 orders of magnitude, but you see that ratio. This is a linear scale. That ratio is very close to 1 for all of them. So plasticity is correlated over very short scales. Those scales are set by the local structure, that even though these have very different potentials, all of these disordered systems are correlated over a very short length scale, okay? All right, oh, and here's the vertex model. Okay, the vertex model also falls on that. We did that later. Okay, the other thing that you see is that if you look at the magnitude of the yield stress versus the Young's modulus, okay, that again is very tightly distributed, okay, around a yield strain of about 3% for all of these different systems. Look at crystals, they're all over the place, okay? But for disordered systems, they're all about the same, okay? And again, that's sort of this, emergent universality of behavior. It's interesting because the definition of dislocation is universal for all crystals. But if you look at how that translates to plasticity, and elasticity, you're all over the map, okay? But even though the definition of softness is not universal, once you look at the behavior, you find things that are universal. Okay, but now, if I go beyond yield, all hell breaks loose, okay? You lose that universality. Different systems do different things. So foams that Doug was talking about, he found that the rearrangements remain localized always. You don't get avalanches, you just get these isolated localized rearrangements and the foam will flow, okay? Other systems, you get avalanches, okay? In other systems, you get avalanches. Still other systems, you see shear banding. So the shear becomes localized instead of the whole system flowing. If you shear like this, you have a linear velocity profile. That's what you get for foams and for ductile systems. But instead of that, what you can get is just the strain all gets localized in a thin layer, okay? That's the shear band. And then you can get fracture. And some others, they don't even shear band, they just fracture right away. Okay, so you see very, very, very different behavior if you push beyond yield. And so what we want to do is use softness to get insight into what's different. Okay, so here is Ludovic Berthier's, Miyazaki Ozawa's configurations prepared by Monte Carlo swaps. So they can take either the system that's quenched from a high temperature, okay, in which you get a stress-strain relation that looks like the ductile system goes up and then it actually levels off. Later I'll show you a curve where the same system where it levels off, okay? And here, but if you equilibrate an extremely low temperature before quenching down to 0 and shearing it quasi-statically, okay, you find this behavior very different. It's quite elastic up to a very high stress, and then bam, there's a huge rearrangement. The system develops a shear band, okay, and then it starts to flow, okay? So that's what's called brittle behavior, okay? You see the strain localization. So that's the system that's prepared by two different ways, from a high temperature quench or a low temperature quench. Here's a different system. This is Doug's system, okay? His postdoc, Hang-Yi Shao, did these beautiful experiments where you take grains of polystyrene beads and you put them at the air-water interface, and there's a capillary attraction between them. So there's a small adhesion, okay? And so you can form these grains into a pillar, and then you can pull the pillar, okay? And so what they vary here are the diameter of the beads, okay? Because the range of attraction is the capillary length, okay? That's fixed, okay? But you can change the ratio of the attractive range to the particle diameter by varying the particle diameter, okay? So they do different particle sizes. I'm going to show results for 1 millimeter and 3.3 millimeter particles. If you look at the 1 millimeter particles, they have a stress-strain relation, which is very ductile, okay? If you look at the 3.3 millimeters, much stronger, much stiffer, okay? But then if you look, they actually show strain localization, and that's the movie. Okay, you can see the strain getting localized and then the two pulling apart. Okay, and here is another picture. Okay, for the 1 millimeter particles, the plasticity is much more distributed. Okay, for the 3.3 millimeter particles, it's highly localized in that band. So that's a different way of tuning it, by tuning the interaction range relative to the particle size. All right, but if you look at the dynamics, if we go back to Ludovic Berthier's system, which is here, okay, here's a system that doesn't show strain localization. Here's the one that does, okay, the ductile on the left, the brittle on the right. But if you look at what's happening, okay, to the system as it's being sheared, in the ductile case, you see these very tiny little rearrangements. I don't know if you can just see them flashing in and out, okay, that occur. So this, all these stress drops can be decomposed into these very localized events, okay? Now let's look at what happens during the huge stress drop that occurs in the brittle case, It looks the same. The only difference is that the rearrangements are all concentrated in this region that becomes the shear band. Okay, but it's the dynamics are localized rearrangements. Okay, and because we have localized rearrangements, okay, a localized quantity like softness, we think is useful. Yeah.
I have a quick question about the right movie. So that one's less ductile.
In the granular case, the larger particles were less ductile. The strain got more localized.
So you cannot see, for example, crack nucleation.
You cannot
See
see
crack nucleation in the
crack nucleation, fracture. Doug, do you want to comment on fracture in your granular systems?
I don't know if you want to call it fracture or not, but certainly the strain is localized. If you go back a slide.
Yeah, well, it does eventually fracture.
See the difference. So the way the strain is spread out. So in the case on the right, literally it will pull apart across that place where the strain is localized. But on the left, it'll kind of flow and it'll neck down and then pull apart. So on the right, if you want to call it fracture or not, but certainly it's strain localization. It's definitely more brittle.
Well, eventually it fractures, it breaks apart.
It's not really snapping.
Yeah.
I think there were foam experiments by Michael Dennin from about 10, 15 years ago, where he studied the ductile to brittle transition in foam. And he showed a strain rate dependence on this. Did you vary the strain rate here? Or was it done quasi-statical?
This is quasi-static.
Thank you.
Which is different from Kai's experiments where she varied that rate. Yeah, very nice experiments. Okay. All right, so we trained softness on these systems, okay? The only difference is that we use support vector regression, which is much less wasteful of data, because you can use all of the data, and we train on something a little bit different. These are technical details that I won't get into. Okay, you can ask about them if you like. Support linear, so we use support vector regression. One thing I do want to mention is that for the very brittle case of Ludovic's data, where that has that huge stress drop, I'm going to skip all this in the interest of getting to the physics. In this case, okay, it turns out that the softness really falls on its face. It's a terrible predictor, okay? So we did something different. We actually trained a convolutional neural network.
Can I ask something?
Yeah.
Yeah, here. So for when you are shearing and looking at plasticity, there is direction dependence. So, and softness is a scalar quantity. Don't you think that you need to put those informations?
It would be good to, and we would like to have that, okay? And in fact, for this, what I'm just about to say, we really should have a tensor and not a scalar, okay? Yeah. Yeah. But we're trying to get by with the scalar for now, yeah.
So I was wondering that what sets that localized versus I mean distributed plasticity. In the last example, is it the capillary length? So if the particle size is below the capillary length, you get distributed plasticity. And
well, it's the ratio. So people have found that if you change the range of attraction and make it small and smaller, you can get more and more strain localization. They don't understand why, but this is an empirical finding. So all this thing about tuning ductility or tuning the degree of strain localization, it's all empirical. Okay, oh, if I quench it to a lower temperature, it's more brittle. Oh, if I shorten the interaction range relative to the particle size, it becomes more brittle. Okay, but why? Okay, and that's what we're setting out to answer. Okay. Yeah. So what are you changing when you're doing that makes a difference? Okay, so here what we do, for this case, we actually train for a structural predictor of the local yield stress. So you can take the neighborhood around the particle, shear it in different directions, and see what is the lowest, the direction which the yield strain stress is the lowest. Okay, these are calculations that are pioneered by Sylvain Patinet. And you can get out the magnitude of that local yield stress. There's a direction too, and this is why a tensor softness would, a tensor predictor would be much better, but we just do a scalar. Okay, so as always, I'm not saying that we're doing the best thing, it's just adequate, okay, for what we're trying to do, and it would be, there are advantages to doing it better. So we actually use the same kinds of network that's used to distinguish cats from dogs, but we train it to distinguish, we give it a little neighborhood around our central particle and train it on these images and get a structural predictor of yield stress, which works quite well. In fact, it works better than softness at predicting rearrangements. It's not trained on rearrangements, it's trained on local yield stress. But if I look at the probability of rearranging versus, I'm going to compare it on a percentile of S or this structural predictor of yield stress, it's Y. What you see is that it's a steeper function. Okay, the probability of rearranging is a steeper function for Y than it is for softness over a smaller range. So it's actually a better predictor of rearrangements. So, you know, and I'm sure one could do even better. Okay, so now what we're going to do is we're going to construct the theory, a lattice theory, similar to what we did before for the Glassy Dynamics, okay? But now elasticity is critical, okay? We have to include elasticity. So this is complicated, but the point is that when I have a rearrangement, I do a bunch of things. I can create, I create a strain. I create a contribution to the strain, okay? But I also have this short range structural change that I mentioned before that changes the softness, okay? There's also from the strain, for the long range strain, that also affects the softness, okay? And then once I have this total strain, which comes from loading the system, from shearing it, as well as from these rearrangements, there's contributions to these strains, you know, I can compare that. The softness gives me a yield stress or yield strain, right? And if my strain exceeds that yield strain, bam, I can have a rearrangement. So it's a complicated diagram, but that's the physics that I'm trying to capture, right? This interplay between softness and plasticity, rearrangements, and elasticity, okay? And what we've done is we've come up with a framework for how to disentangle this interplay for any structural indicator you like, or any indicator that you like. It doesn't have to be structural. So you take your favorite thing, say, I don't like softness. I like this other thing. Just use it. It's fine. It works, okay? So the point is that you can look at, for example, the volumetric strain due to a rearrangement. Okay, put the rearrangement at the origin. What you see is that the magnitude of that volumetric strain decays like 1 over r squared in 2 dimensions. And if you look at the angle dependence, it has this form. Okay, if I look at the deviatoric strain, it again decays like 1 over r squared, but it's isotropic. And I can also, this is directional. I am shearing in a certain direction, or I'm pulling on the pillar. Okay, there's a direction in here. And I can look at the shear strain in that direction. And that has a typical quadrupolar form, very famous in studies of plasticity. Okay, so now I can look at the change of softness. Let me look at the change of softness as a function of distance away from the rearrangement. If I look at the change of softness, it decays like 1 over r squared, and it has this dipolar form. It's more soft where it dilates, and it's less soft where the system is compressed, according to the volumetric strain dipole, okay? So that tells me the softness in the far field is proportional to the volumetric strain, has a piece, the change of softness has a piece that's proportional to the volumetric strain. But it's different from the volumetric strains. The volumetric strain is here in blue, okay? The change of softness is black. You see the two are different if I'm close to the rearrangement. That's the near field effect. And it turns out that the near field effect has a different form. You can subtract off the far field effect and look at what's left. And what you see is that the near field effect has this simple form where I have a coefficient that decays with distance, okay? And then there's something that wants to drag softness to its average value. So what happens nearby, you change the softness, but in a way that wants to restore it to its average value. So it has this sort of form, okay? And then there's Gaussian noise. Okay, so that just emerges from the calculations. Now, people have developed elastoplasticity models where you have on each block I, each lattice site, you have a local strain, okay, you have a local yield strain, and now you just increment the strain, and as you do that, as you increment the strain, once the strain exceeds the yield strain, you say, I rearrange, you set the strain equal to 0 on that lattice site, and then you have an elastic kernel, this quadrupolar thing, right, that distributes strain everywhere else. The strain that was released here gets distributed elsewhere. So you have an elastic kernel. And these things, as shown in work by Mathieu Viart's group, you can tune the system from ductile to brittle by changing the distribution of yield strains, okay? But they put that in by hand. Here, the distribution of yield strains is not put in by hand, it's given by softness. Okay, so yield strain actually depends directly on softness. So I'm not going to go into it, but now we can put this on a lattice. We just put our change of softness. We know, in addition, when you have a rearrangement, not only do you have an elastic kernel that redistributes strain, but you have a softness kernel that changes the softness, right? Both due to the near field effect on spectators and also the far field effect due to elasticity, okay? So you just put that on a lattice, you work it out, okay? No adjustable parameters here. You measure all of these things, okay, either from the experiment or from the simulation. Yeah.
Go back to your the other slide.
C of R, yeah.
Yeah, so this xi that you are, what is it?
It's now eta of R, sorry. Eta of R is the...
No, this other, this C of R on the top. This equation,
yeah.
yes.
Yeah, right. So here we put in the fact that a rearrangement is not a single particle. So it actually, it has some size, which is the correlations of the plasticity, which is the same as the correlations of softness. Okay, which we know is the same as the correlations of softness. So we allow some probability that when this site rearranges, neighboring sites can rearrange with a probability that decays exponentially with that length scale.
But that doesn't depend on your cooling history or annealing history? For example, if you do it better anneal?
It does, because it depends on the correlation length of softness,
and that,
which
that is
depends
going
on
to
that.
take care of that.
Yeah. Okay, so what you see here are pictures from, these are the Monte Carlo swap systems, okay? This is for the more ductile system. This is the map of plasticity in the simulation. Here's the map of plasticity in our model, okay? What you see is that it remains delocalized, scattered all around, okay? Whereas on this case, this is the more brittle case, you have strong strain localization in the simulation. You also see that in the step model, okay? So pretty good. And then this is the experiments. Oh, no, sorry. This is a quantitative comparison. Here's the stress-strain relation for the first case, more ductile, okay, the simulation versus the step model. And the second case, more brittle, the simulations versus the step model, okay? And the average softness, again, you know, reasonably good, and the standard deviation of softness. Okay, so reasonable quantitative agreement. Here's the experiments, okay? On the left, the case with less strain localization, the smaller particles. You see, again, plasticity is sort of distributed all around, whereas for the larger particles, it starts to get localized in the experiment, and you also have it localized in the simulation, okay? Quantitatively, it actually works remarkably well. The step model is the light red, and the experiment for the small particles is dark red, and the larger particles, this experiment is dark blue, and the simulations are the light blue. And again, very good agreement for average softness and standard deviation of softness. Okay, oh, I'm gonna leave out this. All right, so what changed, okay, in these two cases? So in the first case, the Monte Carlo swap systems, what we did was we took each of the parameters that changed from fitting the softness kernel and the softness kernel and the elastic kernel, and we tuned them from the brittle case to the ductile value, one by one, okay? And you see that the only thing that made a difference was the initial distribution of yield stresses, which is exactly the only thing that changed in the system. Everything else was the same, okay? So it was the preparation history that changed. And so, so that checks, you know, that's exactly what we know should happen. And that's what the step model told us, that all those other changes were negligible and the only important change was in the preparation history. Now let's look at the experiment. Okay, again, we changed them all one by one. And the things that matter, I'm going to focus on this one, is that it depends on the range over which you affect the softness of spectators, the near field piece. The range of the near field piece turns out to be roughly the particles, the distance over the interaction range in particle diameters, okay? And that's what changes the system from having the more more strain localization to less strain localization. Okay, so this gives us some insight, right? This is saying, aha, when I'm changing interaction range, I'm changing the facilitation. I'm changing how, if I have this rearrangement, how does it affect the neighbors? Okay, and that's what's giving me more strain localization. So that's a bit of physics that we didn't know before doing this. So that's what you can get out of these models. I'll just wrap it up and thank the people who actually did the work. 3 people. Ge was my postdoc. He's now tenure track at City University at Hong Kong. He did the work on the Monte Carlo swap methods and pioneered the whole step model stuff. Hangyi Xiao is a postdoc with Doug. Hangyi is now assistant professor at the University of Michigan. And Tao Yang was a graduate student with Rob Riggleman. He did a third system, thermal polymer pillars that are being pulled. I didn't talk about that in the interest of time, but you know, that works as well. Okay, thank you.
Questions? Yeah.
I have a bunch of questions, but I'll try to stick to one. Is there a meaningful sense in which you can discuss any of this for purely athermal systems, where the temperature is there to give you kinetics, but pure hard particle systems?
Oh,
the first part, not the
the
plasticity.
first part, can you do it for hard particles?
Yeah.
Yeah, we would like to do it for hard particles. We haven't done it for hard particles.
I see.
Yeah, I mean, you know.
I mean, your laws would be in functions of volume fraction only and not
exactly.
Temperature, but similar considerations. It's just a little harder to talk about barrier crossing because it's purely entropic.
Right.
So,
that's right. But then you should end up with a purely entropic barrier.
Right.
Right?
Right.
Which we should be able to pull out of here as well.
Okay, I have other questions I'll ask you later.
Okay.
Hi, I have a question.
Yeah.
So you said that the softness model did very badly in predicting very brittle materials.
Yes.
You cannot predict where the shear band is or the shape of it. Is it because like in your training, you're not giving any temporal information because shear bands are like cascading events. One is causing the other. There is no temporal component in your training.
Yeah, there are very few rearrangements before you have the huge stress drop. So there wasn't a whole lot to train on, but you can look at many, many, many configurations and look at the tiny little rearrangements that occur before that big stress drop and try to train on those. So we did, and it was enough. We got enough data to be able to train ResNet, which is huge. That's actually a lot of data. So we're not really data limited on that. It's just that, and we don't really understand why, but it could very well be because softness is a scalar quantity that it fails so badly in the brittle systems. And it would be lovely if somebody did a tensor version of softness. Yeah.
So about the second half, the plasticity part. So is there like an I don't know, like ongoing project about like extending to continuum limit? Or trying.
Yes, yes, absolutely. So now we have an elastic kernel and we have a softness kernel. And what we would like to do is turn this into coupled PDEs to have a softness field, elastic field, plasticity, right? And so we can have it turn it into a field version of the theory instead of a lattice version. Yeah, yeah. This is exactly what we would like to do. Yeah.
From the first part of your talk, so when if the system is dynamically heterogeneous and you are determining the softness, so I'm wondering whether the softness will have some domains or it will be homogeneous.
No domains, just this short correlation length.
Okay.
Yeah, the correlations really decay. It's a beautiful exponential. The correlations get slightly longer as you lower the temperature. Okay, and we've compared them. The interesting thing is we have actually compared it to the point to set length, and it increases even more slowly than the point to set length. But the point to set length is a weird length scale. It's not a correlation length. Whereas the softness that's really a correlation length. So, it could be that the point to set, it's really the softness length scale that is increasing as you lower the temperature. That's the important thing.
So I know it's quite tempting for all glass people to use polydisperse model to go to lower temperature and use swap Monte Carlo. But recently we have done a work which is already published where we showed that for polydisperse system, any local property actually gets correlated with the size of the particle. And the size of the particle has a higher, it dominates.
Yes.
So the correlations that we see with different, like we tried with our softness or basically the vibrality, and we realized that, the correlation is more dominated by the size dynamics correlation rather than actually the those parameter and the correlation between the dynamics. So we have to be really careful about looking at polydisperse system and trying to say whatever we see for a monodisperse or bidisperse is what is happening to the polydisperse system.
Yes, and so do we. So for the polydisperse systems, it's quite a projection, right? So what we do is we divide the particles into different bins. I think there are about 10 different bins of radius, size. Okay, so there's a GAB, GAC, GAD, up to 10, right? So there are many, many local pair correlations that enter. Softness becomes a much bigger vector, okay? The dimensionality of softness, the space becomes much bigger. Within each bin, then, we rescale so that we put the first peak, the average first peak at the same place. So we rescale distance to do that within each bin. And when we do that, we can get a reasonable softness that works pretty well. As I say, it actually fails completely in the brittle case. And maybe that's part of the problem is the polydispersity. We don't know. Yeah. Yeah, we don't know what ResNet is picking up on when we train it on the images. It obviously sees the particle sizes. So, it could very well be picking up more on the particle size than on other things. So, yeah, of that. Great, great. Yeah.
So any other questions? Okay, if no, let's thank Andrea once again.